Hello everyone, nice to see you again. And I've been joined by my friend Dr. Bilal Hussein, as usual, because he always attends these sessions. Can you hear me, Bilal?
Yeah, of course I can hear you. Yeah, right.
Let me make sure that my audio is. Bilal, can you hear me?
Yeah, I can hear you now.
Okay. So, welcome again to our live sessions. And today, uh, as I promised, I was going to talk about building a beam, but I'm waiting for others if they want to would like to come and join us because I find it always more of value if someone asks questions while we're building or doing something. Then we can explain things more. Things might look obvious to me, but might not be so for people who are starting just learning about EGSnrc and that's why I appreciate if, I mean, the link for the stream is actually on the descriptions on YouTube, on Facebook. Just click on it and we will accommodate you in our live broadcast here. Okay,
Is this live in YouTube also?
yes, it should be
Okay,
live now. We're live,
okay, okay, okay.
okay, for our watching uh, on YouTube. So if those
Okay.
four, any one of them would like to join us on the stream. So on the descriptions, I've posted the StreamYard link. Just click on it, and it will bring you to the show.
Those who watch on the YouTube will not be able to raise any questions, isn't it? Audio?
Well, they can just type it. They can not
They can
through
type it.
audio.
Okay,
Okay, they can type the questions.
okay, okay,
But I prefer, usually if they click, they join, and then uh, there is a limit of 10 people on the stream with StreamYard, but
okay.
I mean, we can accommodate those who are interested. Okay, so any projects you're doing, Dr. Bilal, or
No, not yet actually. But one thing I did since
okay,
last time was that I put a POE hat on all the raspberries, but I'm yet to
okay,
actually start. Now all my raspberries are on
okay,
POE.
okay. So there are less wires.
Yeah, that's the one thing I did
Right.
actually now.
Yeah, yeah,
I'm
yeah.
just going
Okay, good.
actually bit by bit. I'm not going very fast.
Yeah, this is how I did it. Honestly, one bit at a time, and now I have some even more things I would like to do, but there is just not enough time. Well, I don't have the time now, but maybe in a month or so, then I will start looking back at the cluster. And probably I will just reformat it again and start again from scratch. But this time I would like to actually write the steps and things that I've done. Uh, it's easier, then I can tweak things and so on. So anyway, so we're going to build the Linac as today I promised. Last time we did an X-ray tube, and it was just for educational purposes, and so. But the Linac geometry is a little bit more complex. So let me share now my screen, and I will launch. So let me go to start my Ubuntu virtual machine. Okay. Okay. So Eddie will. Okay. I mean, if you. But then Eddie, you have to. I mean, if you want to. Okay. Someone is has joined us. Okay. So I want to remove myself. And hello.
Hello, yes.
So
Can you hear me?
yes, we can hear you.
Yes, I know. My name is Siti Mileng. I'm from South Africa.
Okay.
I've just started the journey of Monte Carlo or BEAMnrc. So I've been frustrated all week trying to set up a Beam
Okay.
or a Linac. Mm.
Okay. So do you have a Linac at hospital or clinic that you want to model, or you're just doing this, nothing in particular?
At the moment, I don't have anything in particular. I just wanna learn and see how everything works.
Okay.
Yeah, because
Okay.
I tried
So
Beam.
I hope, I
Yeah.
mean, okay. Do you have Beam now running on your computer?
Yes, it's on Windows. I don't know if that's a problem, but I've installed it on Windows.
Yeah, it should be roughly the same. I use it on Linux for other reasons. But anyway, so it's good that you're willing to join us because, especially, I mean, someone like you who's just starting fresh, you can guide us what information we should actually share, with others. Things might look obvious to us, but might not be obvious to many. So if you don't mind, I will keep you on the stream so you can ask the questions, and we'll be able then to answer those your questions. Do you mind if we keep you on the stream?
No, I don't mind at all.
Okay, so now I'm going to share now my screen, and so let's okay. So you can see my screen now, right? The shared Ubuntu, I guess.
Yes.
Okay. So a linear accelerator, I mean, when we, for example, do simulations, let's say for those XYZ, it's one geometry, voxels everywhere, and all what we do is we just define the dimensions of the voxels, and we define the material or medium in each of these voxels. So it's very simple. For a Linac, it's a bit complex because the geometry, let's say for the target, might not necessarily be suitable to model a flattening filter or the jaws. So the guys at EGSnrc, instead of, they made this application, which is called BEAMnrc, where it allows the user to stack different geometries on top of one another in order to model, let's say, obviously a Linac or a Beam. That's why its application is called Beam. In the past, they used to do this through coding. So they had subroutines. They had to write a subroutine to represent, let's say, a slab geometry or a jaw geometry. But now they made it through a graphical user interface where a user will select, okay, I want to use this modules, and then the code will just build the accelerator for you. So just as an example, to do this, we will start. Well, obviously, let's try to see what I mean. I will presume that everyone knows how what's the structure of a Linac. So usually in photon beam mode, we will have a target, we have a primary collimator, and then probably an exit window, then the flattening filter below that, then probably the chamber, mirror, the jaws, MLCs, and probably there is another beryllium exit or a PMMA window. It depends, of course. Obviously, it depends on model of the linear accelerator that you're planning to model. For example, Electa machines, they just have one pair of jaws, and the second, well, they use MLCs to mimic, or to replace a second jaw pair. But variant machines, they have two pairs of jaws, X and Y, and then below that they will have an MLC. So you have to, understand the components or how your Linac is made out of, the geometry. And the difficult part, to tell you the truth, is that trying to get the information about the dimensions of these components. Variant, luckily for us, for example, they make it that make that information accessible through their my Variant website, so you can download some information. And let me warn you, that information is not 100% accurate. Okay, so it's a geometry that that is usable to mimic or to model their linear accelerator. So don't believe, in that geometry they have every bolt, every screw in the Linac actually given to you. No, that's not the case. Okay, so let's start by how to actually create a linear accelerator. So I'm going to open the GUI, the application BEAMnrc. Okay, so when I open it, I'll go to File, and then we will start specify a new accelerator. So now they have a list of component modules in mind to stack above one another to use and represent your Linac. Let's open their website, so at least we can see the document. Okay. BEAMnrc, okay. Maybe I should just ask for EGS. So I'm trying to just open the manual for BEAMnrc, and it's on their website. So let's go there. And if you see the documentation, then let's open the BEAMnrc document. Okay, so this is the BEAMnrc user manual, and the part that is really of interest at this stage is probably the component module. So if we go to, so this is it. So if it's on page, starting from page 138. So these are the component modules that they have. So let's go to the slabs. So a slab, for example, this is the geometry, component module geometry of a slab. And so basically, you can think of them as disks above one another. So if in that geometry you have disks on one another, then you use slabs to represent that. So the thing is that with this geometry, obviously you will need to define then the thickness of each layer in the slabs or disks, and they will all have the same radius. Okay, so we cannot have, for example, for the middle one to have a different radius than the third one or the first one. They all need to have the same radius. This component module is often used to model targets, photon beam targets in a linear accelerator. Then if we go to the next, for example, another one, okay, Okay, these are just, I mean, this is in the old days, because this is how you actually, we used to actually define input for these geometry models. Now everything is through a graphical user interface. This is another component module. So it's called the cons 3R, for example. So in it, you will have only two medium. You can only use two medium in that component module. And there is a medium inside. So this is like a cylindrical symmetry. Okay. So you can actually have, this medium inside, surrounded by an outer medium. This component module is usually used to represent the primary collimator. A primary collimator probably will have just a one line like this, and inside it is probably going to be vacuum, and then in the layer outside is going to be tungsten. Okay, or whatever material the manufacturer has used, for their primary collimator. Let's look at one more. So I hope now the idea is clear. What these component modules? This is a constack. This is more complex now than the cones. The one previous cones. What was it? Cones 3R or 3R. Okay, because the cones 3R you can only have two media. But now with the cone stack, see, you can actually have multiple media stacked on top of one another, and you can use it to maybe, if you want, you can have disks with different radii on top of one another. With the slabs, the disks all disks need to have the same radius, but with a cone stack, you can have different radius now for disks, if you want to model that. This, I've seen people use this to do flattening filters, but really I wouldn't recommend that, because the flattening filter, there is a component module called flattening filter, which I'm going to show now. But this could be used, for example, to represent the scattering foils for electron beams. This is because the scattering foils usually made out of disks with different radius and material. So cone stack probably is what you would be using for scattering foils. This is the flattening filter. Obviously, now it's now you can do more complex stuff with the cones. The previous one, you cannot have, for example, in a given layer, more than two media, I think. There, if we go back, so you would have this, for example, here you have medium 10, and you have this one 11. So only two medium there. 3 is something it's outside. But now with the cones, with the flattening filter, you can have a more, you have the option now to actually have in a given layer different media. And flattening filters, they often made out of different materials. So that's why I would always recommend that to use a flattening filter component module for flattening filter. We have the chamber, for example. Looks it's a bit complex. I've seen people model it. It's possible. Personally, sometimes I just represent the chamber by slabs. I don't go through this complex idea. It depends on what you are actually looking for in a Linac, or why do you want to. Because usually I want to look at those at patient. I'm not looking at those in a chamber. So a chamber, in a Linac, the chamber will just attenuate probably the beam, and will be some sort of source of contamination and so on. So it's sufficient to replace this complex geometry of a chamber with slabs, but it's up to you. Okay. I would recommend to actually model the chamber to do it, not because it gives more accurate results, Well, first you learn a little bit of how to enter data in EGS and so on. But it's the chamber will always, the geometry of the chamber will be fixed regardless of the beam energy you're going to use, or the photon or electron beam. So it's good to have it, and then you use it for that particular Linac for all beam modes. It's not a big deal. But for example, a flattening filter, that will depend, the geometry will depend on the beam you're using, the target also. But the chamber, the components that are other than the flattening filter and the target, they really don't depend on the mode. You know. So you can use a chamber as a phantom. I've never done that, to tell you the truth. I mean, I had no application necessitating requiring that uh, I use the chamber as a phantom. Okay. The documentation is decent. I mean, if once you understand how one is to enter the data, then obviously we have here the JAWS. So the JAWS, it needs a different component module than the ones above it. And we have the MLCs, and the MLCs. So even for variant, this one dynamic jaw, this is for variant machines, because you want to, for example, use a moving jaw. So they have actually a component model. So if in your simulation, your jaws will be, let's say, moving, then you probably need to use a dynamic jaws, or maybe there is another one actually, dynamic variant. Let's see. Yeah, I think this one is probably for, I'm not sure. This is it for Electa machines. These are dynamic jaws, uh, where you can use it for step and shoot modeling, step and shoot B fields. So anyway, these are represented, I mean, in the applicator, in the documentation. So I think that this is sync JAWS probably is for Electa machines, and dynamic JAWS are for varying machines. But probably this is more spelled out in the documentation. And then you have applicators. If you when electrons and cutouts, then you use the applicator as a component model. Okay, so let's go back to EGS, to Beam. And so I want you to imagine the linear accelerator. So probably the first component module we want is called slabs. So I'll click on slabs, and that will, I will call this to be a target. Okay, so we hit add. So immediately a window will pop up with that component module. Then below it, we probably want the cones 3R. So I will select on it, click on the arrow, and then we'll put primary dot collimator. And I'm going to add that. Then we can have another slab. So that's for the window, exit window after the collimator. Okay, so I will call this window. And then we have, I'm doing photon beams, so I obviously want the flattening filter. Let's do the chamber. Okay, I don't have geometry for the chamber, but let's try it. Okay, so we'll add the chamber. Obviously, I'm gonna call it the chamber. Add, and then we have a mirror below the chamber. So there is a mirror component module. And then we have JAWS. So I could use either the JAWS, or the straightforward one, or if it's a dynamic variant. I think this is the one. This is the for variant. So they have variant MLC and then dynamic JAWS, and then yeah. Oh, sorry. This is the MLCs. So this is the JAWS. If I want to use the dynamic JAWS, but I would just use the stationary one. JAWS. Okay. Then we will have MLC. Okay. It depends on what you want to study. If you really want the MLCs added, if, for example, you're just doing stationary or stationary openings, beams, and you have variant machines, obviously you don't need MLCs. Then just don't add it to your Linac. So I'm gonna maybe I'll skip it. I will not add it, and I will leave it. So what else? So after the JAWS, we need that's the beryllium, or not the beryllium, the PMMA exit window. So we need a slabs component, and I'll call it exit because I have one with window. So I'm gonna call it exit, and probably we need air. Okay. So once I stacked my component modules of the Linac, then I can save and close. One thing I should warn you about is once you generate this, you cannot modify it. If there is something wrong, you need to just delete the accelerator and start fresh over again. Okay. I'm not talking about the input files. Probably this will be obvious in a few minutes, but I'm just talking about, for example, if by mistake you entered the chamber was actually above the flattening filter, then this is wrong. Okay, you just have to delete everything you've done and repeat everything from that's why it's first, it's a step you need to do carefully at the beginning. And I've also seen people, for example, they would generate an accelerator for a given beam. For example, you have a high energy, let's say 21EX machine or a true beam or reverse HD. Okay, the components of the Linac are essentially the same. So I mean, we have target, we have a primary collimator, and so on, but the dimensions might be different. Okay, so what I've seen people doing is that for each beam they generate a Linac. Well, I'm not saying there is something wrong, but actually you could just generate one linear accelerator for photon beams. And then in the input file, where you specify what are the thicknesses, the dimensions, and the materials of these regions in the Linac, that would be depend on the beam mode that you are planning to run the simulation for. Okay? So, yes, you have a question?
Oh my goodness, I've been typing them all out. The first one was the slabs. You said, well, I remember one of my friends was investigating like different materials inside a target. So I was just wondering if you cannot have multiple media at the same level, can you use that other one, the cone stack, to create a target with it?
You will understand now when I start to actually talk about how you make the input file. This is still geometry, okay? And honestly, for a target, I don't think you need to actually have different materials with different radius. Why would you need that? Because usually the beam is a very narrow, it's a pencil beam. It has a dimension of 1 millimeter or so. The electron incident on the target is maybe around, has a radius of 1 millimeter. So why would you need to then have different radius of discs, okay, to represent your target? Doesn't make sense. You see my point?
I see it now.
Yeah. So I will show you now what you. That's why usually slabs for target, it's there is nothing wrong of using the other component model. I'm not saying it's wrong, okay? But what I'm saying is it's not necessary. Let the geometry be as simple as possible, okay? And reserve the complex geometries where things are really complex.
Okay.
Okay. Okay. So now suppose I have these are my
Okay.
Linac,
Before, sorry, like you said, once you save, you've saved. So now, if you, what's the influence of the mirror in there? Is it still the same as what we expect? I don't know. Is it
nothing.
just geometry?
Okay. It's just a geometry. I mean, I just put it as just to show people that, okay, yes, there is a mirror, but but the mirror, typical mirror thickness is very, very small. It's very thin. Okay. So essentially, does it really matter in electron beams? I don't believe so. So maybe the electrons get scattered because, but the thickness is very small. Okay. And I don't believe in photon beams. Obviously, I mean they have an effect. So if you don't want to put it, it's fine. That's okay. But it's simple. You're going to see a mirror geometry is very simple. So usually I will put it. Okay, it's not a big deal.
Okay.
But you're going to see now. Okay.
All right. Thank you.
Okay. So suppose that these component modules now represent our Linac, then obviously I'm going to save and close. Okay, so we need to give it a name. Okay, so I'm going to call it demo. Okay, and this is where, although it's not necessary at this stage, but probably it's going to ask you where is the PEGS data file. So remember, the PEGS data file is a file that has cross sections and stopping powers for the materials that are going to be used in the simulation. There is a new feature, I think, in EGS. I'm not sure does it works with Beam or not. Yes, you can actually go pegless, but I've never used that feature. I don't know how it works, to be frank. But basically, so I'm gonna just use the standard, let's say 700 that comes in the henhouse folder. So 700 ICID, because it has a list of geometries. Obviously, if you're doing something for a real Linac, you would probably want to contact the vendor and ask them for information about these component models, especially the target, the flattening filter, and so these are very important. Okay, so I'm going to select that. So the first thing you need to do is, after we have generated those stack of we need to go to execute, and we need to compile the linear accelerator. Compiling the accelerator, basically it's going to build an executable file that we can use with different input files to run simulations. So because, I mean, when we build the accelerator, basically it's going to, there are predefined subroutines that define these geometries. Now is going to just grab these subroutines, put them in one single file, and also include the physics, all of the stuff needed for running simulations, compile it in one file, Mortran file, and then you create an executable from that. So here I'm going to hit build and compile. So this is what it has done. It went and grabbed some subroutines and them just on built actually the input file for our not the input file, but the Mortran file, this file for our Beam demo. You don't need to worry about this much, okay? But so done. Now it's building it. It's going to generate an executable for our Linac. And obviously it has actually generated a folder now. So if you go to your EGS home area, so let me show you. So EGS home, you will find a folder. This is a bug. I know it went, and I don't think it's a problem. Okay, so if you go to the EGS home area, now you will see a I feel this. You will see a folder now. Starts with the word beam underscore and then the Linac name or the beam name that we have used. So in our case, we have used the Linac called demo. Obviously, I have other Linacs that I could show maybe at the end of the stream, but we can go inside, and these are the Mortran or Mortran files. I'm going to try to compile it actually from the terminal. So I will just go to the directory. Okay. And once I'm there, I can just type the word make clean just to remove anything that has done, and then now type make. So now it's compiling, building and compiling. Let's see. I don't know why the GUI gave me an error in doing that.
I don't know. I've also gotten some errors because I had it on Linux and I got the same error. And I went to Linux, Windows and I get the same error. Then I saw on Reddit they say.
Yeah, sometimes it does not like certain naming. I know this is with Linux. So maybe the plus sign that I have used, maybe it does not like that. So
no, actually normal. I have seen that this type of thing is a bug. I think it comes, but still it is working fine.
You're sure? Because it gave me an error. It did not compile. So let me try again. Demo module. I think it does not like this plus sign. This is one thing. So I'm just going to replace with an underscore. And let me just new window. Okay. So I'm just going to remove the directory, beam, and then demo. Okay. So I can just type here beam build. And then demo without module. So now this should build, get that directory again. And then make, let's see if it's going to work now. So I think there are no problems. Probably the issue you had in the names of this component module, you probably maybe use the space or use the character that it does not like. What I would recommend is for a space, you use an underscore. Don't use plus signs. Don't use a dot. So I think it's due to the naming in when you have named the component modules. And the error that I think produced this was I had the exit plus air. So the character plus character, it does not like it, like to see that in the names. So when I replace it by an underscore, I think now it's going to work fine. Let's hope. Let's wait. I'm not getting errors, but it's compiling is building is going. I mean, it's taking some time.
Okay. Sorry, I saw you edit some file there to change the plus.
Yes.
How do you get to that level?
Okay.
Obviously, you've been using.
Okay. Okay. You see, this is a warning. That's not, it's not going to. I mean, that's not a problem. I will show you. I will show you what I've done. Okay.
Okay.
You're good with using terminals and editing text files. You have no problems with that?
Yes, yes, I'm
Okay,
good with that.
okay, okay, okay. So in basically when you generate what we have done, these component modules, all what the application did was to actually generate a small text file that has a list of the component modules of that Linac, as well as the name tags or titles for these component modules. Okay.
Yeah.
This is how we used to do it in the old days. We used to actually make that, okay, you see, building was okay now, no errors. So this is how we used to do it in the old days. Where is that file? If in your home area under EGS_home, there is a folder called BEAMnrc, small letters, and then inside that folder there is another folder called spec modules. So I'm going in that folder and let's list what I have there. These are actually the Linacs that I have built or compiled. Okay, these are the text files listing the component modules of these Linacs. So the one we have done was actually called demo. It's this one. So let's go and see what's inside. Okay, what's inside that file? Okay, see, this is the file. It starts with this first 2 lines: component module CM names, and then it has actually the names for these component modules. Remember, we had slabs, cones 3R, slabs, flattening filter, chamber, mirror, jaws, slabs. And then we have we provide, or we gave an identifier for each one of these component modules. So the second line will have the identifiers or the names of these component modules. So now this is the target that corresponds to slabs, primary collimator to this, windows for this, and so on. Okay. So what I've done is, first I deleted the accelerator because something building was not correct, something is not right, and I went into this folder and I opened the file, and then I just, the plus that was in here in this word exit air, I replaced it with an underscore. You could, for example, just delete the file completely and go back to the graphical user interface and go through the process again. But of course, you need to be careful with the naming and so on. So what I think, if you are having problems, the problem is in the naming. It's probably, look in this line here. Look at the names you have used. If there is a space, probably that's the mistake, because it might think that, because you see all of these identifiers, they are separated by space. Okay, so if you, for example, if I use here flattening filter, the system will think flattening is for one component module and filter is for another one, and then you will end up with more identifiers than actually the component modules that you're using. Okay, so I think that is the source of the error. Make sense?
Makes sense.
Okay, so please check what you have done and fix it, and probably it's going to be work. My advice: don't use spaces. To clarify the words, use underscores. Don't use dots. Don't use commas. Okay, don't use pluses or these funny symbols. Just regular characters and underscores. Okay. Okay. Now, what I've done after this, but probably the command might look different in Windows than in Linux. But once I've modified this file, let me go back to the folder. Okay, so this is the folder which had the component modules. Okay, so the next step is I type the command beam build, and then I put the component, the name of the Linac, but you should not use the extension. So just the name. This is what you should do. For example, once you hit this, you see now it's saying, okay, I'm overriding, because already there is a folder with that name, so it's overriding it. But you can actually build the accelerator just everything from the command shell. You don't need the GUI, but people like to use the GUI. That's fine. Okay. So now our Linac is ready. Okay, so Beam. We have CD, it's in the X, okay, and then Beam, it's called demo. Okay. So we have an executable. So what's the next step? The next step now is to define the geometry of these component modules and the material and some other stuff. Okay. So let's open. So we can load the previous accelerator. Okay. And we should find demo. And when I load it, I will get this window. This window is where I'm going to actually define my input files. So let's see if I have. Okay. Okay, let's share screen, and I wanted to share something. So I have downloaded from Varian, let's say their Linac. And okay, so let me share this with you. Okay. Okay, so this is their. Can you see some? Okay, can you see it now? Yes, I think it's there. So this is something you can download from my Varian, where they have provided some information for their Linux. Okay, this is for a low energy linear accelerator. Let's close this. Okay. And of course, the geometries, these are not for EGS, but this you can use them for with Giant, with MCMP, with they give you this. So if you read and go through it, so they will give you something like this, okay, where it shows, for example, the flattening filter, the jaws, where is this jaw? This is the flattening filter actually here. These are this is the target, and these are the primary collimators, and so on, even the MLCs. So this is the basic geometry of their Linac. And they might have some additional information about, let's see if the targets. Okay. I don't know why it's okay. Okay, so this is some information about the flattening filter. Obviously, it's an RZ geometry. So all what they need to do is just give you a bunch of points, okay, to represent or to mimic. And I think here, these are the X and Y coordinates for these points. So point 1, 2, 3, 4. So these are the points 1, 2, 3, 4, 5, and this is the x and let's say y or the height, or it's actually z in this case, coordinates of these points. So that information, usually when I want to actually translate this information into EGS, I would make a nice cup of coffee, piece of paper, and start to draw things and so on. Be careful. Sometimes, and I'm not sure now, sometimes they give you this information in inches. So I'm not sure if this is in inches or this is in centimeters. Just be careful about that. Okay. So obviously, if it's in inches, then you need to change it into centimeters and so on. So I don't have that information. I don't know from where to get it. I would always ask a question. Okay, these are the dimensions, but what's the units of these dimensions? Is it centimeters or is it in inches? So they probably will have it somewhere in their document. This is a flattening filter, by the way, for a 4MV. Okay. Now they have another flattening filter. This is now for a 6MV. So also see the energy. That's why you can actually have one linear accelerator built, but then you can have different input files for depending on the beam. So if for example, doing a 6MV, then you would obviously, for the flattening filter in the input file, you would use these dimensions or coordinates for that. So that's 4 and 6. Okay. What about the target? Do they have information about the target? Physical wedges, that's all technology. Okay. I've never actually modeled physical wedges at all. But I'm trying to see, okay, the targets, what's the material? So obviously, this document has information about 4 and 6MV. So I just want to look what the target. So let's search. Because flattening filter, okay. But I'm looking for the targets. MNCs. Okay. I don't know where the targets are listed in this document, but I'm sure it will have information on the targets. For sure, it will have information on the targets. Okay. It's somewhere there. It's just I have to dig for it. Okay. This is okay. They do have, for example, there is another document. Let me open it, share it. Another document. This is for their high energies. So this is the document for high energies, and let's hope they have information about the targets there for the high energies. Yes. So here, for example, that maybe there is that information is actually well, here there is a target, a 4MV. Okay. 4MV, tungsten, copper, and then they have the dimension here, okay, or the thickness. This is the thickness. So 4MV will be made out of two, it's a slabs, but two layers, tungsten and copper, each one with its own thickness. A 6MV, these are the thicknesses for the 6MV and so on. Now, the question I have is, are these dimensions in centimeters or in inches? It's not. Oh, here it's actually clearly stated, so it's in centimeters. That's good. So, for example, if I want to do a 4MV, let's go back and try to do this in a 4MV. Let me share back again. So stop the sharing and we'll share again. Okay. Okay, so here, now the slabs is the target. This is where I'm going to hit edit. And if you hit the help, I mean, the beam does have actually quite a good help. So this is the geometry of the slabs component module. Basically, all what you need to define is the number of these slabs and their thicknesses. So imagine we're going to call just above the target. That would be where my zero or my reference is going to be. So now with this window set, the previous component model and it has zero. Obviously, this is the first one. So we'll just say, yes, that will start at 0. That's fine. Now, half width of outer square boundaries. Okay, I can put 20. This is basically the boundary of the component model. It's not the dimension of the slabs themselves. It's just, okay, what I mean, an outer boundary. And here I'm going to put target. I can put some information. This is a 4MV target, for example, tungsten and copper. And the distance of front of material in component reference plane, obviously, this is 0. So the reference plane is, we're going to define it, is just above the target, and that would be the 0. So the question now, this is what's the distance of the top of this component module to the reference plane? Obviously, it's going to be 0. The number of slabs, we have 2 slabs, define the layers. Okay, so we need to just enter the data from the document and put it here. I'm just going to put, because I cannot, it's going to be tedious to go back and forth between the 2 documents. So I'm just going to put something like 0.01. Okay, and this is the material of, so the first layer was a tungsten. So tungsten, okay, and then I have another layer. So one is 0.1 millimeters, the other one was 2 millimeters. I don't know if these thicknesses make sense or not. Okay, but obviously the manufacturer has provided the thicknesses. That's the ones that you should be using. But I just want to demonstrate to you how you can actually enter these materials. And now this is copper. Okay, I'm selecting. So obviously the media or the material, those are the ones listed in the PEGS data file that we have listed. We have selected at the beginning. Now this is done. Okay, I can preview it. It should give me 2 layers with 2 colors. This one is going to be tungsten. This one is going to be copper. And that's it. Okay, if we even took the radius to be 20, maybe we don't need that. Actually, we can put it just 5 centimeters. Okay, because remember, on the target, the beam is going to be narrow. It's almost like a pencil beam. So it doesn't matter if you put it 5, 1 centimeter. It's not really a big deal. So once I've done that, my recommendation, because this is going to take some time, is once you have finished one component module, try to save it. So we'll go and save input parameter as, and we'll make sure that we're saving it in the same directory of the Linac, and I'm going to call it, this, for example, is going to be my 4MV. Okay. Fine. Complaining a lot of things because we haven't put a lot of things. So that's the slab. Let's go. So obviously, what one needs to do is to go through each of these component modules. So the cons3r, there, when you open the window, it will tell you, okay, when we open this window, the previous component module ended at this distance. So this is outer boundary, title, this are primary collimator, and distance of this material. Yeah, you have a question?
So inside that title, you can use spaces now and pluses and whatever you want.
Yes, that is not because this file is not going to be compiled. It's not going to be built. Okay, not a problem. It's going to be read, but not being converted to an executable. That's not a problem.
Okay, thank you.
Yeah. So the distance, obviously, I mean, if I'm going to put this to be 0.1, of course, when we run the simulation, it's going to give us an error because, of course, there is an overlap between this component module because this is the distance of front of material to the reference plane. So obviously, there cannot be an overlap between this material and that material. I can make it further away, for example. For example, suppose this component model does not actually start where the previous component model ends. That's not a problem. I can put this to be, this actually, let's say it starts at 2, it's 2 centimeters away from the reference plane. So the component module, the targets above it, had dimensions of 2.1 millimeters, but this component model is going to start at 2 centimeters. That's not a problem. Okay. So the number of points used, again, obviously, if you're a beginner this, and you can have the document, but there is the help. So this is all what we need to do now is for each of the points that we're going to use to define this component module is obviously we need to put the Z and R coordinates for these points. So if suppose this is so for the primary collimator, suppose the thickness is going to be 5 centimeters. That means it's going to end at 7 centimeters away from the reference plane. Okay. So the number of points, probably I don't need a lot of points to define the primary collimator. 2 points is going to be enough. And different points. So just give me a minute, please. Okay, I had to answer the door. Okay, so 2 points is going to be enough. Usually we will calculate these 2 points so that the primary collimator has an opening of, let's say, 56 centimeters at 100 SSD. Because that's the diagonal. I mean, the maximum field size is 40, usually for a Linac at 100, but we always have to think of the diagonal dimension. So roughly that's 56. I think it's 40 times 1.414 or square root of 2 gives you around 56. So you can put roughly the primary collimator to be at that point, so that that's why you need a calculator. You need a calculator to calculate the coordinates of the line, so that this line will give you a divergence of 100, let's say 56 centimeters at 100. Okay, so we need to calculate what's the coordinates. Obviously, the z coordinate is the first point. This is going to be at 2, and the other one. So this is going to be at 7. Let me check something. I just want to see the help. The z, is it from where? Is it from? Because this sometimes is crucial. So also the first and last point must lie at the z boundaries of the z values are measured from the front of the accelerator, not from the front of the component module. You see, this is the point. So now z needs to be at 2, okay, the first point, because it's the coordinate, z coordinate, from the reference plane, not from the component module, relative to the beginning of the component module. And r, this, I would just use the trigonometry just to calculate what the r should be at the first point and the second point, such that it gives me a diverging, parameter. I'm just putting numbers here so that at least in the preview we can see how it looks like. But obviously, and again, this component module will not change with the beam mode. The target will change, the flattening filter will change, but not the primary collimator. Okay. So now, suppose these are the coordinates, then I'm going to hit OK. So the material inside, this is probably vacuum. Okay. And the material outside, we're going to select, I don't know, tungsten. Let's use tungsten. Okay. And then I can hit preview. This is now the geometry of the primary collimator. Okay. And it's starting from 2 centimeters. Yes, 2 centimeters there. Okay, so we just make sure that we want this, the divergence of this line to be roughly around 56. Or what you can do is just look at the manufacturer document and use what they have given in that document. I often get that question, and I would say just use the 56 rule, because this is a primary collimator. It's not going to affect your beam quality in the center and axis, I think. But anyway, okay. So we have done that, okay, primary collimator, and then we have the exit window. This is probably a beryllium exit window, and then we look from the document where its location and the thickness of that exit window. So you can do this. The toughest component modules to put is probably the flattening filter, okay? Because there you need to, there are a lot of points that, and that document you need to get that information. So this is the toughest. The chamber is also not easy to enter, but that's why in my case usually I would just go with 2 slabs, thin slabs of copper. But if you want to model the chamber, then you would need the chamber component model. The mirror, this is a simple one. Again, so the mirror, let's say the distance is, let's see, 20 centimeters, okay, from the reference plane, and the z-span. So, okay, it's not the thickness, it's the span, how much it spans in the z direction. So let's suppose it's 2 centimeters, and mirror top. We can either define. So let's look at the help. So we can define either what's, this is the span of the mirror, and we can define either, I think, the coordinates, mirror, yeah, from the first layer, or we can actually use, I think, define this angle here, angle. So let's x coordinate of mirror at top. Let's look at that. From Z to first layer. Okay. Usually, sometimes when I don't understand the geometry well, I would just put numbers and look at the figure. Okay. And I think between these two, okay, yes. So it's basically, it's the coordinate. I think it's this. I think it's this coordinate. Okay. So we have to, for example, from the top, we have to give the coordinate of this point, and then for the bottom, the coordinate of this point, and then it's going to calculate automatically what is this angle. Because sometimes the vendors, they would just tell you, okay, the mirror is, let's say, 15-degree mirror. So you would like to check, okay, with these coordinates, giving you a 15 degrees or matching that or not. Now, after we have made this correct and the tilt is correct for the mirror, now we can enter the layers. So here, obviously, there are, I think, let's say 2 layers. So if I put 2, for example, then I can go and define the layers. The first layer, what's the thickness? Obviously, this is going to be something small, and that could be, do you have PMMA? Maybe PMMA or mica. So if material is not there in the PEX data file, obviously you need to create that material and add it to the PEX data file. And this is another one. So okay, let's use anyway. I need to just give the thickness. Okay, and obviously it's not going to show anything because the thickness, the true thickness of the mirrors it's very thin. And this is outside. So here we need to provide some additional things is outside of the mirror. So yes, we have defined this mirror, but what's the material here and what's the material here? Obviously, the mirror will be surrounded by air. So we're going to just select air there. And preview. There's attempt to, okay, that all numerical values are, okay, what am I missing? Anything? Yes, here. So we need to put like 20. Title, this is a mirror. And preview again. There's something missing. It's trying to make sure that there is. Okay. I don't know what I'm missing. It's region improve preview. Please make sure that all numerical values are defined. Okay. I don't know what I'm doing wrong here. 20 half width title distance. Okay, 20 is 2 centimeters. This is 1. Maybe here I need to put -2. Review it. Okay, define layers. I really don't know what's the problem I'm facing. The position of the. Oh, I see. I know the problem. The problem is this, I think. Okay, because we did not enter any information about the previous component module, it's complaining because this is unknown. I cannot preview it. Okay. So I'll open another Linac, and then we can look at that Linac. So obviously one needs to go through each of these component modules one by one. Okay, the JAWS, Again, this is probably one of the simplest component models to enter. So we have, let's say, we're doing a true beam, or a variant Linac. I have two pairs of jaws. Orientation. This is an X, and also is I. Okay, we need to then enter the distance of the jaw, the front and the back. So obviously, the difference between these two is going to be the thickness of the jaw. So for the X is going to be different than the Y. We could, once these are entered, then we can actually use this box now to define the opening. Okay, so here is just where the top and bottom reference planes for or the top of the jaw and the bottom of the jaw. But then we need to define what's the x y coordinate of the opening. So here, for example, this is the jaw. This is the top reference. So this, for example, suppose this were the x jaw. This value here is the distance from the reference plane, which is just above the target, up to this point. Okay. Usually, I think it's 35 or something centimeters. And then the back of the jaw, it's the distance again from that reference plane up to the bottom of this jaw. Now, the opening of the jaw is defined by the x coordinate of this point. So now this is the sentinel axis. If this is, let's say, -2, and this is -3, taking divergence, this will diverge and give a certain field size, let's say at 100 centimeter. Obviously, these are not the coordinates that we put here to define the points are not, let's say, a 10, a 5, and -5. So 5 and -5 is not going to give you a 10 by 10 field at 100. These dimensions needs to be smaller, and you can just use trigonometry to calculate what should be the x coordinates, either plus or minus, for each jaw in order to give you the desired field size at 100 centimeter. So you could do that calculation, or you could use this nice little tool. So this is the lower field edge. This is basically the opening. So if, for example, I want a 10 by 10, I'll put this to be my -5, and this is 5. And the SSD, that's the plane where I want, things to be calculated, the dimensions to be calculated at. Obviously, we want this to be at 100. And the focusing of the jaws, this is going to be at 0 at the target. So once I have these, I would select apply this to the jaws that I want. I have two pairs. Now it's going to give me an error because I don't have the values entered for the x and y. But let's give an example. Okay, so let's put 35 and let's put 41, for example. Okay, and this is going to be 41.5. I'm just making numbers, so these are, might not be true. Okay, so and then I will go to define x, and let's try this again. Okay, and then update the x and y coordinate. It automatically calculated what should be the the x coordinates of and front and back of the jaws, such that when it diverges, the divergence defined by the jaw is going to give me a 10 by 10 field at 100. So this is a nice tool. I would recommend using it. But you can actually just get a piece of paper and you can calculate it using trigonometry, and you will find that the tool will give you exactly these values. Okay. Now the material of the jaw, again, tungsten, okay, or whatever material that's for, and so on. Okay. Now, when you have finished these, we need to, obviously, every time you make a component module, try to save your work. Then we need to go back to this main okay. So someone is enter the stream. Hello there. Hello. You can unmute yourself. Okay. So anyway, if you have questions, PIC, if you have any questions, please just stop me and ask the questions before I move on. Okay. Let's go back. Okay. So now let's go back to this main input parameters. Okay. So here, obviously, we can give a title for our linear accelerator. We can say for MV, okay, 10 by 10, because it says for a specific JAWS settings, maybe 100 SSD. I will explain this shortly. SSD, and so whatever information you want to put there. Okay. Now, this is the medium that the geometry or the linear accelerator or EGS is going to use when we do not define a specific material or medium for that geometry. For example, remember we had some, let's say between the component module 1, the target, and the second component module. So the target in our case had a 2 point something millimeters, but the second component module started at 2 centimeters. Okay, so there is a gap. Now, what should be filled in that gap? This is the material that EGS is going to use. So vacuum, we could use that. Okay, but sometimes you have to be careful. You have to look and see, does that make sense or not? Because if I used air, for example, usually I like to use air. The problem now, when I think about what I've done, is that between the component modules, between the target and the second, the primary collimator, there should be vacuum. It shouldn't be air. So it's going to actually put air in that location. So the trick to do is, okay, just make another slab below the copper. So remember we had 2 slabs, tungsten and copper, up to 2.1 millimeters. So in that case, I would make a third slab below it, okay, with a thickness that will take the total slab thickness to 2 centimeters. And I will define the material for that slab to be vacuum. And then air could be used to represent, some other areas in the Linac. So these are some of the things you could do in order to get your geometry more and more accurate. Obviously, if you use air instead of vacuum, I don't think that's a major difference, to tell you the truth. But it depends on what you are looking for. So that's the material. iWatch, this is something, you just leave it none. There used to be an application called EGS Windows. I have failed to actually install it on my Ubuntu installation. That is basically a tool that will use to visualize the geometry, in 3D for your Linac. There is a website by Dr. Dave Rogers where he has shown the Linacs that he has built, an example of these Linacs, even some tracks for particles. And he has used that application to actually get these nice images. But it does not work with, or maybe it's me, someone managed to actually install it on. They used to actually distribute it with EGS, but they have stopped, I think, from 2017 or 2018. So anyway, but if someone managed to actually run that application, then you can specify that, okay, when I run the simulation, I want, the output, you make an output so that I can visualize it with this application, the EGS Windows. Okay. Okay. Random number seed options. You can always click on this. Obviously, I mean, I don't know everything, and this is maybe it's used to a way, for storing what random number seeds, the seeds for your random number generators, and so on. So I mean, usually these are topics for really advanced, very advanced users, and it does not have any implications on the simulation. It might be a very good tool, for example, if you want to report a bug, because to reproduce the bug, the problem is you obviously need to run the simulation with exactly the same seed. So, for example, you have built your accelerator, and then you found the bug, there is something wrong. You can then send this information to the guys for EGSnrc, and you can send all of this information, and probably they can recreate the error regenerated, and maybe help that helps in fixing the code. So just leave it, and the general rule is use the defaults. Unless you know what you're doing, then you change it. Run options this first time. The options are okay, we can restart. This is a nice thing about EGS, is you can always restart the simulation. So imagine we have done, let's say, 1,000,000 histories, and then we found, okay, I need more particles. Then you can just come and modify the EGS code, sorry, the input file, and select restart instead of first time. Okay, so it's as if you're continuing the simulation, accumulating more histories, okay, on what you have already on your results, not to start from all over again. I think MCMP does not have that option. I'm not sure about Giant4, but this is what I heard. MCMP does not have that restart option. Maybe I'm mistaken about this. So first time. So obviously, when you do real work, you would either select first time, or you'll come and change this to restart. Okay. Parallel jobs, that's something used in older systems, and analyze previous if you want to reanalyze previous run. Okay, output option. Okay, this is the most important thing Beam is used for, is to produce what's called phase space files. A phase space file is a file that contains information of particles reaching a certain plane. Usually for a linear accelerator, we would like to run the simulation and then register and record the particles reaching, let's say, 100 centimeters from the source, or 70 centimeters, let's say, from the source. So that's the file that will have information about the particles reaching there, about their statistical weight, about their charge, about their direction and location, and has some other additional stuff called batches, which I'm not going to explain or go into today. But that phase space file, if you want to run, let's say, a simulation in a water phantom, or in a patient, or any different material, let's say to generate a PDDs or profiles, then you can use the phase space file instead of using running the simulation through all of the Linac again. So you can just take the particles from the phase space file as source and run, these particles in the geometry of interest. Obviously, that's a very good technique. Let's say if imagine if I'm running a simulation, I want to investigate, let's say, something in a water phantom, in a different material, in a chamber, but all of these, they will have my beam will have a 10 by 10 field setting, and let's say 6 MV. So instead of for each of these simulations in the Phantom to start the simulation from the target, okay, then we can generate just one single phase space file, and then for we run the simulation using the particles reaching the phase space file. Of course, this was the philosophy quite some time ago. Nowadays, personally, I would not actually use phase space files. They take space, and computers now are fast. So the time it takes for the computer to open the file and read from the disk information about that particle, it's probably the same time that it's going to just model or simulate the particle from the source, unless you have probably a fast disk. But personally, I stopped actually using phase space files unless there is a specific reason that I want to generate a phase space file. The reason why I stopped actually using the phase space file, one of the reasons is there is always the limit. I mean, usually you would need to, if I'm going to have a phase space file that represents, let's say, a 10 by 10 field, obviously I need to have a lot of particles there. And that will end up, you will have a large phase space file of maybe I think 1.5 gig or up to 2. I've seen larger ones, larger sizes. So then if I want to share this information with any one of you, I mean, that's 1.5 gigs. I would rather send you the input file and you generate either your PEGS file or just simulate directly from the input file. But I leave that to you. But this is one of the important, actually, outputs of Beam, is to generate a phase space file. Store data array, I'm not sure what that is, so I leave it yes, as if. Latch, I'm not going to talk about it today. Maybe next month we can set an example of how to use Latch. I want just to run a simulation, but Latch is a powerful tool, so I'm going to set it to no latches. You can leave the default; it's fine. It's not a big deal. Score last Z. This is if you want to an additional. For what reason? Of the reason you want to record with the particle the last Z that it interacted at before it reached, I think, the phase space file. Then you can record that coordinate. Sometimes this is important, sometimes it's not. I haven't actually used it in my work, but that's up to you. Maximum CPU allowed. This is the default 0.99. I would recommend you just change this to 500. Maximum CPU hours allowed. Basically, it's you can stop the simulation through. Obviously, you can tell the simulation simulate 100, let's say 1,000,000 particles. That's one way. It will just needs to do all of these particles, and then it will stop the simulation. Another way to stop the simulation is you can tell it, okay, these are 10 million particles. These are 10 billion particles, but please run the simulation only for this amount of time, of 1 hour. I really don't have time. So it will run simulations at 1 hour. It's going to stop the simulation. Or if it reach some statistical uncertainty, this usually with those RZ and those XYZ simulations. So usually I control everything by the number of histories, and I keep this. I think the maximum is always 500. Okay. Okay. This is probably the incident, the most, also now we're doing photo. So I want to select what's the incident particle. I need a source of my, of source of transport. What's the source for photon beams? Is an electron. So I'm going to select the electron. It's going to be a particle, and these are the source numbers. Okay, there are various source numbers, that probably a lot of them I don't really know. Okay, they're in the manual described, but the one that is usually I use either a point source sorry, not a point source, a parallel beam from the front. I use that one. Or an I assume people use the elliptical beam with the Gaussian distribution. That's also, in some situations, this probably I'm going to show maybe next time also, is you can use a phase space file actually as a source for simulations in beam. So here, for example, I'm going to use a parallel beam, and then if you click on help, it will explain, where is the help? Okay, let's wait. Let's take it, let's put again 0. Okay, and let's hit the help. Okay, so this is how it looks. So all what we need to obviously define is the radius of this parallel beam and the direction. In our case, the direction is just going to be hitting, it's perpendicular on our target. There is not, we don't need this angle. Now to define this is we need to look at several angles, okay? So there are three parameters, the V INC, W INC, and U INC. These are, I think, the cosines of the angles between the beam direction and the X, Y, or Z coordinate. Since I want my beam to be shooting downwards, then the UINC, this is obviously going to be, this is a 90 degree, so the cosine of 90 is 0, okay? We have, with the V, okay, VINC is the angle between the x-axis and, again, the beam axis. So in this case, it's also going to be 90. Remember, the beam is down, so the VNC is going to be this angle like that. 90 cosine of 90 is 0. And the WINC, this is going to be 0. So cosine of 0 is going to be 1 because the direction of the beam is going to be parallel with the positive z-axis. Okay. So when I go back here, the beam radius, this is a parameter vendors or manufacturers are not going to give you, by the way. Okay, so anything related to the beam, they're not going to give you that. The source, is it parallel or is it elliptical? They're not giving you that information. Okay, even the energy of the particle, they don't give you that information. They give you the geometry that this is a 6 MV or whatever, but the exact energy of the, because obviously they can't. Okay. So the way we validate that the energies and the geometries and these things are okay is once we run the simulation, we produce percentage depth doses and we compare the percentage depth doses with measurements. If they match the measurements, then we're happy with our modeling of the Linac. If they do not match, then we need to come back to the model and change the beam. So a 6 MV, you could, for example, change the beam a little bit. Okay, I'm going to use 6.1, 6.2 MeV or lower. About the radius, if you have problems with the profile penumbra, then maybe the beam radius instead of, I think this is in centimeters, so this is going to be big. So the millimeters use this. So the X and Y, this is going to be Z, 0 and 0. Okay. Okay. And the last one is going to be on. These are the cosines. And the beam energy, we will start with something like 4 MeV because this is a 4 MeV Linac. I'm just going to put 4. But don't expect the PDDs to match. You would be lucky. Okay. If they do not match, then probably come and change here and run the simulation again with the 3.9 or 4.1, depending on how you want to alter the PDDs produced by the simulation. Okay, so that's done. Then what else? Photon forcing. This is where we define, okay, how many phase space files do we need? I need obviously at least one, so I need one. And then I have to define the component module where the component that we're going to score So the phase space file is going to be scored below that component module. So if I'm going to, let's suppose this is a standard, I want the phase space file below this exit window or the slabs. So we just need to count. This is 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to put this to be 8. And the zone type, I really don't know the difference. I just select the squares, and that's it. Okay. Those calculations, that's not really important now. Maybe later on, next time, I can explain more about it, depending on what you would like to do. But for example, remember when I said the chamber, you can use the, if you want, to use the chamber component module, probably you want to actually know what is the dose in the air within the chamber. So there is a way to actually define, okay, I want system to record what's the dose in these geometries or these regions, and this is dose calculation. Do you want actually the total dose or those components with it? Those components, I think, is related more to the latches. See, everything is connected. So I prefer that we keep this for the next time. But for the time being, we just want to run a simulation. This is where we define, so the reference plane and the Z of the first component model to that reference plane. Obviously, in our situation, it was the target. And we said we're going to use this above the target. That's going to be our reference plane. This might not always be the case. If you're, for example, modeling a cobalt teletherapy machine, maybe that's a bit different. Okay. The last thing is, okay, we have the EGS parameters. This is where we control the physics. To say the least, the most important thing is you need to make the boundary crossing algorithm exact. There's Presta one, but you need to make sure this is exact, and electron step algorithm exact too. They keep these options because for whatever reason, you see each one represents a different algorithm or a way how to model electrons, transport of electrons especially. I'm talking about this boundary crossing and electron step algorithm. So sometimes you would like to reproduce, obviously the modeling has improved. So there are newer algorithms with more accurate physics. But suppose you want to reproduce data that was generated 25 years ago. Okay, so you need to have access to those subroutines that were used to actually produce those results. You want to show, for example, okay, now whatever was calculated there was wrong or maybe insignificant. We have used better physics, but still did not change. Whatever you want to use it for. So this is where you can say, okay, no, I want that paper, 30 years, they have used Presta 1, they will usually define what other parameters they've used in the simulation. I'm going to use that. And then you can come and change the physics and use different or more latest or more accurate physics and run a simulation with that. That's also fine. So the three, if you want to use the latest, exact, Presta 2, and the spin effects. Okay. More information on the physics, you can find it in the manual, or maybe the help here will give you some notes. But more details are actually found in the EGS, not in the BEAM manual, but in the EGSnrc manual. Obviously, they have cross sections. If you want to use NIST cross section, this is Beta Heitler or NRC. You see, they have introduced more accurate physics and so on. Boundary and the physics will depend, of course, on the problem you are trying to simulate. So obviously, when you're doing high energy bound compton scattering, probably Kleine-Schiene is going to be enough. Because using bound compton scattering is just going to take more time in the simulation. For me, I usually use the latest physics all the way. I know it's irrelevant, but now computers are really fast. So I don't care a lot, okay? Pair angling, so you can play with these physics the way you want them, radius scattering on or off and so on, okay? So once you have finish entering this, then you save, and then you can preview your accelerator. Obviously, because you not right put everything, you can preview the accelerator, and then you can go to run and execute. So let's open the demo that is okay. So with Beam, there is a two Linux actually demos. I have brought them, and so load the previous accelerator. I think the first one is the EX 10 MeV. Okay, I'm not sure. This is probably okay. This is probably the Electron one. Okay, let me open the Photon. I think the Photon is the 16. Load. So this is the 16 MV. P is for photons and E is for electron beam. Okay, browse local. If I remember, we have used the 700. Okay, so obviously they have used lesser number of component modules. Now what I need to do is to load an input file. They actually provide an input file, so I just need to go to that directory, the 16 MB, and then yeah, this is the input file. The files, if you're interested, you can always find them in the henhouse area. So where is my henhouse area? CD, okay, henhouse, and then under henhouse there is a folder called Omega, and then anything Omega is related to the Beam. Okay, so then under it there is BEAMnrc, and then we have the BEAMnrc examples. Okay, there are two Linux. You see, there is this is the photons, and this is the electrons. So let's go to the file for photons and list what's there. So you will find this is the module file. First thing you need to do is you need to copy this file into the Beam in your home area under BEAMnrc spec modules. Okay, remember that. So usually you will do copy, and then I will select home area, EGS home area, and then remember there is a folder called BEAMnrc and spec modules. That's where we had the demo. We need to copy this file there. Once it's there, we can open it with the GUI, and once you open it, these will pop up. So obviously I have it loaded there. That's why it popped up. So once you have you load it, then you build the accelerator. So it will create in the home area a Linac, which is called Beam, capital Beam, and then there is a EX16 P. That's the folder that has input files for the accelerator. The next step, what you need to do is we need to copy this into the accelerator folder. Okay, so this is what I've done, and so if I open now the input file, okay, then we'll go to there, and this is the input file. Okay, so now the slabs, if I go there, slabs, for example, they will have information, tungsten target, whatever, the layers. Okay, and now I can hit the preview and can preview the full accelerator. So this is the target. Obviously, I think this should be vacuum, but this is the flattening filter, for example. Okay, this is probably the chamber. Okay, here is the mirror. It's obvious. And then we have the jaws, and then we have air slabs. So these are slabs that takes us from here all the way up to 100 centimeter. Okay, so this is actually a slab component model. Then we can run the simulation. So usually when you do a Linac on your own, expect a lot of errors when you run the simulation, and you just have to read what you have a problem with this component module or something is missing and so on. So, but obviously with this input file, everything should work. So when I execute, okay, so it runs, okay. There is an error. Okay, why is there an error here? Warning is going plane one has 0. So sometimes it gives you some errors. Let me, probably I modified something. Let me actually copy the file again. So I'm going to copy input file. Okay, we're going to copy it into that accelerator. Okay. So if there is something wrong, then it's EGS guy's fault. I think I modified the component model, but let's use what they have actually provided. And by the way, if you went directly and open an input file, it will load the accelerator for you directly. Beam, okay, we'll use this. Okay. So let's execute and run. Okay, so now it works. Once you see batch 1 started with 1, 2, 3, 4, that means the simulation is running now. Okay. There used to be a number here on the side. I don't know where that number go. Okay, because that's the number that tells you the number of particles in the phase space, unless there is no phase space file. But I think there should be a phase space file. So I just let it finish. So at the end of the simulation, it tells you, gives you some information that look, this is the elapsed time, 53 seconds on my computer. With this time, probably I can do 1 million, I can simulate 1 million history per hour. Okay. And then, I can estimate, for example, okay, when I started with 1 million histories, how many particles in the phase space file, and work around and see. So let's look at, obviously, if I want to analyze phase space files, I use the BEAMnrc application. So let's look into, let's say, the scatter. Okay, particle type all. Okay, fine. Linear 0, maximum. This is 20. Large, none. Okay. So let's remember that the phase space file. I want to see where are these particles that reach the phase space file. So this is the file, and out. Okay. Now, if you're a Windows user, then you probably you get I mean, it does not execute XM Grace automatically once you analyze the beam the phase space file. But here, obviously, this looks like a 10 by 10 field because I can see the particles in the phase space file. A lot of the particles are actually between -5 and +5 X and Y. So it tells me, okay, this is I mean, this you use it just, I mean, don't do 1 million or 2 million particles because you will get everything here screen black because it just records the particles. And obviously, the particles in the middle are going to be much more, you will receive more particles in the middle than at the edges here. But my recommendation is just run a small simulation and see, it gives you an indication if there is a something, a major error, let's say in geometry or not. Okay. So I guess we are almost now, okay, we are at 2 hours mark. I'm going to stop now and maybe just if there are any questions, before we conclude today's session. If there is any question or something you probably want me to cover more on the next time, please let me know.
For me, that was nice because like I said, I read all the books and stuff, but actually seeing it and hearing from your experience what what you can skip, what you cannot skip, that was really nice. I really can't ask you any questions more. I need to actually sit in front of this thing and just try to figure it out and make sure something runs.
Yeah,
But
my
so far, thank
suggestion,
you
I
very
mean,
much. Clarifying a lot of things.
so this will be actually on my channel on YouTube, and we have done many of these actually before, but I've been getting questions people would like. So obviously, I would like, for example, if you don't mind, if you join us next month, and once you join us, then we can, for example, you can show us what you're doing and what are the errors you're getting, and maybe we can help you with these things. Uh, that would be nice. Or you can actually, and I hope you can tell us your success story. You can show us what you have done, and oh, it works, and I'm happy, and so on. And then we can take it to the next step. Okay.
Okay.
So,
So far, everything, everything is clear so far. So far, that's nice.
yeah, expect. I mean, expect you're going to have errors. Okay,
Mm.
you will learn by as you with experience you will learn what these errors mean and so on and so on. Obviously, till today I make some errors, but I quickly recall, okay, I got that error and that was the reason, and I go and fix it. So that is something you gain by experience by doing it. Don't let an error to discourage you from doing anything. Oh, just actually it should push you more. Okay, I want to do it better and more and so on. Okay.
Yeah,
So
yeah.
I was
Thank you.
at your I was at your seat, and probably at that time probably I did not have a lot of people to teach me how to do things, so I had to read manuals or with my colleagues, students. But eventually I got it, and now I'm I'm sharing this information with others. So I'm
Mm.
sure one day you're going to do exactly the same thing with people who don't know how to use EGS. You're going to explain everything to them, and the more you explain to people, the more you obviously learn yourself from this. So next month, I wish if you can join us, and uh, your questions were very helpful to me to guide me where I should focus. I really like that. I appreciate it, and thank you very much.
All right. All right. Yeah, I'll try to recruit some of my friends to come to the
Sure,
stream as
sure,
well.
sure, sure,
uh,
sure. No problem.
okay.
Bilal, how was it? Yeah, we can hear you, Bilal.
Yeah. Oh, what was it? What did you ask me?
No, I just how was it this time today? I think it went smooth, and
It went
obviously I
very
cannot.
smoothly. In fact,
Yeah,
yeah, no, actually, it was very good. Actually, in fact, like you said, it will be more useful for the newcomers to learn the things,
Yes.
so that they can get to
Yeah.
know the things. Naturally, they have to actually learn it by mistakes only. But what I felt is only one thing is I have been telling you also that it is like we can draw that and show that what is exactly that one. Like I like to actually normally teach it on the whiteboard, so that will be actually more easy to visualize it actually.
Yeah.
So see the things where the primary collimator will be there. So what should be the exact, what should be the exact minimum, that maximum. Those things we put it on the draw it on the paper or something like that, so they'll be able to grab it more easily.
True. I'm just sometimes a bit cautious, to show data, provided by vendors without, they're agreeing that I broadcast it or show. That's my only problem, my only concern.
No, no, actually
Okay.
not that. That's what. No, no, no. I don't want to show that the variant data or electro data. You have to
Yeah.
just construct a generalized actually a collimator. You can just
Yeah.
show that what should be normally. There should be a filter. This much the thickness should be the normally. It should be varying within
Okay.
this one. It could be of any
Okay.
material. That's a different issue.
Okay. Okay. I will do that. I will prepare a present. You're making things difficult for me, so now I have to prepare
No, not at all.
a PowerPoint presentation to show at least, and to take it one step at a
No, no,
time.
no,
I don't
not
mind doing
PowerPoint.
that.
I'm not asking for PowerPoint. Like you used to show it on
Yeah.
a paper, draw it on a paper. That was more effective. I found actually.
Okay. Okay. Then I need to get a camera, an overhead camera.
Oh.
Okay.
No, no,
At
I
least
don't
now
want to make you.
I have now a green screen behind me.
Yeah,
Okay.
I can see that. I can see that. I can see. I
I
found
have
that you
these
have
now.
changed. I thought that you changed your room, or maybe that you are sitting
No,
in a
that's the
different.
same. But you see, I have these, like lightnings, one on each side. So now I need to get an.
You are improvising
Yeah,
yourself actually.
yeah. So now I get to get an overhead camera. That's fine.
Yeah. No, that I found was little easy to see what exactly
Yes.
because
Oh,
by looking at the help is available, but even by drawing it, it is very easy to understand.
yeah. No problem. No problem. Okay, then. In this case, probably we need to conclude now. We've been live for 2 hours. I would like to thank all of you who joined me, and your comments are always welcome. And I hope I see more people joining the stream and asking questions and so on. That's really will help me a lot and I don't claim I know everything, but some of your questions might challenge me, and then I need to go and dig and see how to solve that problem. So please come and join us. Join us anytime, and thank you very much. Okay.
Well, thank you so much. Thank you so much. Good night.
Okay. Good
Thank you.
night to all of you. Okay. Good night to all of you. So see you next month.
Good night. Yes,
Okay.
definitely.
Good night. Okay. Good night.
Uh,
Bye bye.